6.3 lesson. So we've discovered that delta G is Gibbs free energy, and it's the overall evaluation of whether a reaction wants to happen, so to speak. Now, you do have to get it going, but will nature keep this going? Is it thermodynamically favorable, or do you have to keep on pumping energy into it in some way? So if delta G is negative, then the free energy of the system is decreasing, which is what nature wants. So it is thermodynamically favorable. And I know the workbook keeps saying spontaneous, but I don't think the test ever actually uses that word. It loves thermodynamically favorable, which means if that's negative, it will proceed in the forward direction, and it will do so until such a time as it runs out of activation energy. Like if you throw water on a wood fire, or it runs out of reactants, like you burn up all the wood, or you choke off the oxygen. And in that case, what that means is that Q is less than K at equilibrium. Go write down the products over reactants, the power of the number in front, and then if Q, your snapshot K math, is smaller than the given value for K, for instance, we're about to work with this one, then you don't have enough numerator, you don't have enough products, and to even try to get to equilibrium, the reaction has to proceed forward. So all this turns around in this column. If G is bigger than 0, then the free energy is increasing, which means you have to keep on pushing it along. Not like fire, for instance. Fire keeps self-supplying, but the opposite of fire would be like anti-fire, like creating the paper, okay? Now, I know that's a bit silly, but if you're creating the paper, you have to keep pushing and pushing and pushing. The paper does not self-assemble in any way, right? You have to keep putting in the effort. The sugar in an orange did not self-assemble. It was pushed along through the photosynthetic reaction powered by the light hitting the chlorophyll molecules, right? It is very much non-spontaneous. It is not thermodynamically favorable. It is a huge reduction in entropy. That reaction stores energy into the sugar molecule, and it also gathers carbon dioxide, which was running around easy and free in the atmosphere, and water, which up in the plant and swimming around, and takes the carbon and the oxygen and the hydrogens and makes them into a tiny little sugar packed full of energetic bonds. And those atoms are tied in much more than they were before, and those bonds are much more energetic. So in both senses, that's a reduction in Gibbs free energy that is a non-spontaneous, a non-thermodynamically favorable reaction, and it will stop as soon as it gets a chance, as soon as the light stops, right? Which means it's thermodynamically favorable in the opposite direction, and sugar will burn. You give it the activation energy and it will turn itself back into its constituent components, right? And so that means if something wants to run backward, that Q must be greater than K. And again, visualize the fraction. If Q is bigger than K, what that means is you have too much numerator, you have too many products. This thing wants to run backward. Now, right there in the middle is what if G equals 0, delta G equals 0? Then the free energy is not changing overall, which means you're at equilibrium, which means it doesn't favor either direction. Now, to be fair, that means that in many cases, it's running both directions, but at least it's doing it equally. So it's not actually going in reverse or forward. And in that case, Q equals KEQ. That's what K being true means. K is only the truth of the system at the moment if it's at equilibrium, which means that Q, the math at the moment, must be equal to K at equilibrium. Down here, we have a reaction. So we also know K, and we know delta G at 25 degrees Celsius, or 298 K. All right, it's a positive. This reaction at this Kelvin temperature does not want to just proceed. Now, there might be some temperatures at which it does, though, huh? And that brings up this equation here. This is the delta G for the reaction at the circumstances you are using right now. This is delta G standard, see the little circle for the reaction, under the circumstances that were given as the standard conditions. This R is just an adjustment mathematical factor, otherwise they aren't equal, and it's given there. Now, also I should point out, in the reference pages of the test, there are at least 2 and maybe 3 R values. You're going to need the one that uses joules per mole Kelvin And you know it's going to be joules because delta G involves joules. Now, the ones that you use in PV equals nRT do not involve joules. There is no energy component to that equation. So this is the one where you do need joules. That's temperature in Kelvin, and that is natural log. And that is the Q value, so the K math at this exact moment under the conditions you're talking about. Now, that's not going to come up in this table, but we'll certainly circle back to that. So here's a reaction, and let's look at what we've got. We know that K is this, all right? So if these are our pressures right now, then this is the product, this is the reactant, so we get this squared over that. Well, it turns out that that's 0. Q is definitely less than K, which means the reaction wants to go forward. You don't have enough numerator. And if we take these circumstances all and put it into here, we'll find out that the current delta G under these circumstances is a negative number, which confirms again that this reaction wants to go forward given the chance. We change the numbers, we still get the same kinds of answers. Now at this point, this squared divided by that gives me 0.09, but that is K. So Q is equal to K. So is K true? Yes, K is actually true. In these circumstances, K is true. Well, that must mean that you're at equilibrium. And that must mean that delta G for the reaction in these circumstances is 0. And then everything from there on, as the circumstances change, means that Q is bigger than K, which means you have too much product. And it wants to go in reverse, and you're going to get a positive delta G value when you put everything into here. Now, we basically just discussed these two paragraphs, but it is interesting on the last one. One of these is the standard state. And I'll tell you what, I missed it the first time, but it's true. What is the standard state for reactions like this? It's when Q is 1. And at this point, this squared is that. And so when you divide this squared by that, you get 1. And remember that a fraction of a fraction gets smaller. So this is going to get smaller. And it turns out that you land on this. And so Q is 1. That's the standard state. That does not mean that Q is equal to K. K is at equilibrium. And the standard state is when Q equals 1. Those are not the same thing. At equilibrium, K is worth whatever it is. Remember, in this case, it was worth 0.09. But for the standard state, if we're going to plot the delta G naught here, the standard state, Q is 1. That's all a bit messy, and I would write that down and have a think about that. Of course, you can always ask additional questions. I don't remember anything like this from the test, and I'm going to skip it. On the back, they want to talk about delta G standard and how that relates to K, and we've talked about some of this. Now, this does get a bit hairy. I would hit pause and think and write some stuff down. Delta G standard is reported when Q equals 1, not when K equals 1. When Q equals 1. Remember, K is just whatever it is at equilibrium. It could be any manner of things, and it's only true at equilibrium. The delta G number is reported, though, at whatever circumstance it is, such that Q will equal 1, not at equilibrium, presumably. And then we can talk about what that tells us about K. So if delta G standard is less than 1, then under standard conditions, the reaction wants to go forward. But remember, we said it's also true that when delta G standard is true, Q is equal to 1. But for a reaction to go forward, K must be bigger than Q. So if this wants to go forward and Q is 1, then K must be bigger than 1. If delta G is bigger than 0, then this reaction is not thermodynamically favorable. It wants to go in the reverse direction. But remember, at the standard conditions, Q is 1. If the reaction wants to go in reverse, that means that Q is bigger than K. But Q is 1, remember? So Q is bigger than K, or K is smaller than 1. I'd like to talk about these equations, and more fundamentally, we start off with this one. Now that's delta G of reaction for whatever circumstances you have going on at the moment. Here's delta G standard, which is not the same thing. Remember, that's when Q equals 1. And this is R, which is the adjustment mathematical factor with the joules in it. It's 8.314, as we see down here. And that's in joules, remember, and that can really throw things off. So make sure that you are always paying attention to the joules versus kilojoules. That's the temperature in Kelvin, and that's the natural log of Q, which is, again, products over reactants to the power of the number in front in your current circumstances. Well, if this was at equilibrium, then delta G is 0. So then we get this, don't we? And then if we subtract this over, we get a negative version of this, and then we could just push the negative over there, and this is the version on the reference sheet in the real test. It's the only one given in the test. However, I really would not put it past them to use a version that essentially needs this. Getting from there to here, it needs to be a skill that we have. So what we would do is take this part, divide it under, and then take inverse natural log of both sides, which is e to the power of natural log unzips, and it all disappears. And we just get KEQ. Then we have e to what looks like the left side over here. We just pushed it around to the right side. E to the power of, and don't forget the negative because we divided by a negative. So this whole side became negative, and it's still negative in the exponent on e. So then what I would do is assemble these values, this divided by that, get a numerical value and do inverse natural log. And for crying out loud, don't forget the negative. Inverse natural log of that value, and that is K for those circumstances. For example 2, we have this reaction, and notice that we go from 3 molecules of gas to 2, so that must be a reduction in entropy, and in fact, the standard delta S value is a negative number. So we're told the delta H standard, delta S standard, even delta G standard, and the temperature. So what's the value of KEQ at 25 degrees Celsius? Now, again, this is the version in the booklet. In the real test, we have to get to the point where we can generate this. So find a tutor, find a video on doing logs or something, but we need to be able to get from here to there. Assuming that we've got this here, that we know that, we can proceed and we can put in the delta G value. I've converted it to joules here so that it cancels correctly with the R value that is on the reference page in the test. And here's my Kelvin temperature. Do not use Celsius. So this divided by that gives me this as an exponent. Then I take the inverse natural log, which is the same thing as e to the power of, and I get K. For B, we're asked to find KEQ at 100 degrees Celsius, and it's really tempting to say, well, we'll just do the same thing as A. But even though we're allowed to assume that delta H and delta S don't change with temperature, delta G is definitely going to change with temperature. Plus, we weren't told to assume that it doesn't change. So we don't know delta G standard for 100 Celsius or 373 K. So we would have two unknowns here and here. So we're going to have to go fill in this hole in our information. So we'll use the Gibbs free energy equation because above I was told delta H standard, delta S standard, and T I know is 100 Celsius or 373 K. Put in the values and I'll convert this to kilojoules by pushing the decimal left 3 spots. So I'll use negative 0.187 kilojoules per mole K, really. And we'll get this value for delta G standard. Now I know this bit. R again, same R is in the reference page in the test. T is now 373 K. This divided by that gives me an exponent on E. I'll do inverse natural log, and I get this if I use the unrounded exponent. I think we got 8.6 E17 if we use the rounded one. So at what temperatures would this process be non-spontaneous or non-thermodynamically favorable? Well, that's when delta G is a positive. And since this is effectively the same thing as delta G, it's mathematically equal. I'm just going to use this portion of it and put in the values I was given at the top. Don't forget that's the negative and that's also a negative, and set it greater than zero, positive number. Now this converts this to kilojoules. When we divide by 1,000, we push the decimal point left 3 spots. And then the tricky thing about inequalities is remembering when to reverse them. When I add this across, I don't reverse it. But when I divide by a negative, I do reverse it. It reverses here. And then I can multiply by -1 on both sides, and that reverses it again, and T is greater than 1059K.